So thank you very much, everyone, for being here. Today's speaker is Enrico Cinti from the University of Urbino and University of Geneva, and he will be talking about space-time emergence inside the black holes, inside black holes. Sorry, apologies for that. It's plural. And he was originally meant to give a talk with Marco Sanchioni. Unfortunately, Marco couldn't make it for today. So we thank Enrico twice, first for being here and second for arranging a brand new talk for our seminar. So Enrico, it's now up to you to start, and there will be Q&A after your presentation. Thank you very much for accepting the invitation.
Thanks, Silvia. Thanks, everyone from the Proteus team for this invitation. It's a pleasure to be here. So as Silvia was saying, today we'll talk about some issues having to do with space-time emergence when we are dealing with the interior of black holes, essentially. And in particular, with the interior of black holes in IndiaCFT and holographic theories more generally. So this is just an outline. And the idea here is basically the following, that you have many approaches to quantum gravity, which they seem to suggest that space-time, to some extent or other, cannot exist at the fundamental level. And philosophers have tended to analyze this kind of situation by saying that space-time is supposed to be emergent in quantum gravity. And the understanding of this specific relation of emergence is supposed to be one of, if not the main, conceptual hurdle to an understanding of quantum gravity and how quantum gravity relates to our world, to the world of the manifest image, if you want. The idea, when it comes to space-time emergence, is that space-time emergence is connected to an issue that Agate and Buttrick have emphasized, which is the issue of empirical incoherence. And empirical incoherence basically concerns the meaning and possibility of measurement operations understood as events localized in space and time, in a theory without space-time. Here, the idea is, you're maybe familiar with it, it's reasonably straightforward. The idea is that if I assume that measurements and measurement operations are essentially something that needs to happen at a certain place, a certain time, it is extended for a certain period of time, and then I record the result of my experiment at the end of this procedure, again, in a certain place. The recording is stored in a certain place. These are all spatiotemporal locution. And I cannot really make sense of this if I don't have a space-time to interpret what is going on here. And the answer that is being given since the work of Agate and Buttrick and later on, the idea here is that in some sense, it is not necessary that space-time is there at the fundamental level, as it probably is not in quantum gravity, but to account for experimental data, we just need to rely on an emergent understanding of space-time. So if at the scale at which we carry out experiments, we have space-time, then we are reasonably safe. We can interpret our experimental procedures and understand them using the emergent space-time that comes out of the microscopic quantum gravity degrees of freedom. And then the point essentially becomes how to understand this emergence relation between an emergent space-time and a fundamental quantum gravity level. And you have various strategies in the literature. One is developed by Vincent Lam and Chris, and they basically suggest a form of what they call functionalism about space-time. And here, in a slogan, what they want to say is that space-time is as space-time does. And they basically avoid empirical incoherence by applying a kind of functional reduction to space-time degrees of freedom and interpreting them in terms of the appropriate limit of a certain quantum gravity collection of degrees of freedom, then behaves appropriately, behaves just like space-time should. And then by the functionalism in their approach is just space-time. Another approach has been suggested by Sam Barron, and he suggested the kind of space-time eliminativism, he calls it. And his idea is that basically the status of space-time, general relativistic space-time, is essentially analogous to the status of Galilean space-time when we are studying special relativity. So in special relativity, we don't really wish to say that when velocities are small, Galilean spacetime emerges from Minkowski spacetime, what really we should say is simply that Minkowski spacetime, in the limit where velocities are small, is just a very good, very well approximated by Galilean spacetime, or even perfectly approximated by Galilean spacetime. And in this sense, we can use Galilean spacetime to describe what is going on, but really Galilean spacetime does not exist. It's not there. There's Minkowski spacetime, which in a certain limit behaves in a certain way. And again, this approach basically avoids empirical incoherence because we can specify, that's the idea that Baron wants to defend, that we can understand things like localization and other properties are required to make sense of experimental data by basically taking an appropriate limit of quantum gravity, and in that limit, checking that indeed it basically approaches arbitrarily close general relativity, and if it approaches a general relativity arbitrarily close, then we can have something at least approximately like localization, and then that is supposed to be enough. Now, what I will do today is that I will discuss some of these issues in the context of the IndiaCFT, which is, if you're not familiar with it, basically the main approach to an holographic theory of quantum gravity. And in particular, I will look at what happens when we're trying to describing the interior of an evaporating black hole in this context. Because a lot of strange things happen. You might be familiar with this. You might have seen some of the recent computations that have come out. A lot of strange things happen when you try to describe the interior of a black hole in a DSCFT, and you kind of get something that is really different from what has been discussed in the literature thus far. In particular, what I'm going to stress is that emergence really as a whole does not work as a concept to understand the relation between the semiclassical space-time level and the fundamental quantum gravity level. And that rather you need to rely on something that I call operational recovery. And the idea of operational recovery is that basically only operational data makes sense when it comes to the semiclassical regime of IndiaCFT, where we are supposed to get space-time. And I will then suggest two basically metaphysical glosses on operational recovery, one that I call operational eliminativism and one that I call operational emergence. And the difference basically between these two approaches to understand this idea of operational recovery is that they differ in whether or not you take space-time as a posit to be reducible to operational data. And then I will sketch how a DSCFT understood in this way avoids empirical incoherence, despite not being allowed to rely on emergence, strictly speaking. So let's start. Let's start with a brief technical recap of the issues. I'm going to basically give you a very quick introduction to IndiaCFT and to some of the models for the interior of a black hole. So the idea of IndiaCFT is a duality. That is, it's an equivalence of theories, roughly, between quantum gravity in an anti-de Sitter spacetime. Now, anti-de Sitter spacetime is the maximum symmetric solution with negative cosmological constant of the Einstein equations in n+1 dimensions. Quantum gravity in this spacetime is supposed to be equivalent to a conformal field theory in n dimensions, so 1 dimension less, which is defined on the asymptotic boundary of this ADS spacetime. Now, as a slight note here, IndiaCFT is indeed sometimes referred to as the only known non-perturbative definition of quantum gravity. It is certainly one of the most studied non-perturbative definitions of quantum gravity. It is the main approach to the holographic theory of gravity. Nonetheless, it should be noted that anti-de Sitter spacetime has a somewhat significant restriction, which is that you cannot really do cosmology with something like anti-de Sitter spacetime, at least not the kind of cosmology that we're interested in. Anti-de Sitter spacetime just does not model our universe on large scales. Our universe is de Sitter spacetime, which has a positive cosmological constant. Nonetheless, the idea behind studying something like IndiaCFT is that you can ideally learn some general lessons, which include the kind of bulk reconstruction that I'm going to discuss in a moment, that in principle should be applicable to more general cases. So they're not, strictly speaking, supposed to be restricted to anti-de Sitter spacetimes. So as I mentioned, at least insofar as we believe, and we have reason to believe it, that a CFT is a well-defined object non-perturbatively, via this duality, we have a non-perturbative understanding of quantum gravity in anti-de Sitter spacetime. Now we can use this CFT basically to define the non-perturbative dynamics of the theory. Since we can do this, since the non-perturbative dynamics is ultimately supposed to be the fundamental component of the theory, we will speak equivalently of CFT or fundamental description and ADS or semiclassical effective field theory description, since when we will speak of ADS spacetime, we'll basically only be interested in the semiclassical gravity description of anti-de Sitter spacetime. So a description where you're not really studying the full quantization of gravity in this spacetime, which, except for very simple example, is actually not even known. We're just studying basically general relativity with some quantum corrections, perturbative quantum corrections. So something that I should specify is that there is no claim of relative fundamentality intended by this language. So, of course, this is a duality, so these two things are supposed to be equivalent. As Yar and others have stressed, there is not really a sense in which we can say that the CFT is in some sense more fundamental than ADS, or the boundary is more fundamental than the bulk in this situation. All that I mean to say is that we'll always study the CFT as the relevant, as a non-perturbative object, and we will only look at ADS as an effective field theory describing semiclassical gravity. So in this sense, one is more fundamental than the other, not in the sense of the boundary being more fundamental than the bulk. Now, just to get an idea of why in this context we can speak of a non-spatiotemporal fundamental level, the idea here is that the non-perturbative dynamics of quantum gravity in ADS are dual to CFT quantities. Since they are dual to CFT quantities, they can at most depend on conformal structure, and so they will in particular not include any spacetime structure that is stronger than conformal structure, which is, you can debate whether conformal structure is enough to speak of spacetime, but certainly it is very different from anything that we're used to when we speak of spacetime. And it is quite different from normal general relativistic spacetime, normal gravity. Now, moreover, if we take the common core approach, as most of the literature seems to agree we should, to interpreting this duality, so we should just commit ourselves to features which are invariant among the two sides of the duality, so invariant between the CFT and the ADS, then we get an even stronger result that not even the dimensionality of the spacetime in some sense is a physical piece of data. It's really something that we should not be committed to. Now, if not even the dimensionality of spacetime is something that we can take seriously, not curvature, because curvature is not invariant. The CFT lives in flat spacetime, while gravity in ADS presumably involves some kind of curvature, some kind of dynamical metric, which is not there in the CFT. Then it really seems that whatever the fundamental degrees of freedom that you're dealing with that are supposed to be described by this common core really have nothing to do with spacetime as we're used to it. There really is nothing of standard geometry that is left in the description. Now, this leaves us with a problem in the sense that if the fundamental degrees of freedom are not spatiotemporal, then we need to know how to recover the spatiotemporal degrees of freedom, and in particular, spatiotemporal degrees of freedom in the bulk. Now, this problem has been studied quite in detail in the literature on the IndiaCFT. There is this lovely review by Daniel Arlo in 2018, and the program basically to recover local bulk quantities from the fundamental degrees of freedom that we encode in the CFT is something that is called bulk reconstruction. And it is crucial to understand the emergence of spacetime in IndiaCFT in particular, because it tells us how the emergent quantities in the bulk semiclassical gravity theory are connected with the fundamental non-perturbative quantities that, as of now at least, we only know as things that exist in the CFT, from which this spacetime is indeed supposed to emerge. So in a sense, it gives us the bridge between the CFT, which is at the bottom, is the fundamental piece, and the semiclassical gravity, the effective field theory that we described in the bulk ADS spacetime, which is spatiotemporal. Now, the crucial bit for bulk reconstruction, the crucial piece of this project, is something that is called entanglement wedge reconstruction. Basically, what entanglement wedge reconstruction says is that given a certain spatial subregion B in the boundary, there is a bulk region, WB, which, if you want, you can define somewhat precisely, but for all intents and purposes, you need to simply know that it is a bulk region which is actually extended beyond simply the causal domain of B, such that all physical quantities in WB can be encoded in the CFT by operators in B. You can think of this also as something that is sometimes called subregion-subregion duality. So if you give me a certain subregion in the CFT that we call B, I can encode all the data included in a certain subregion in the bulk spacetime called WB. Now, an important aspect of this thing is that the map between WB and B, so the duality map, which connects a certain region in the CFT with a certain region in the ADS bulk spacetime, is always a linear map, but it is not required that it is an isometry, in the sense that it does not need to preserve inner products. The way that you should think about this is that we can associate an Hilbert space with the CFT and an Hilbert space with the semiclassical gravity in ADS spacetime, and then we can define maps between them. These maps need to be linear maps, but they need not be isometries, so they need not preserve the inner product between two vectors in this Hilbert space. And basically, the way that these failures of isometry emerge is that we evaluate this map in perturbation theory in the gravitational constant, and these failures of isometry come out as non-perturbative corrections. Maybe the most famous, at least the most studied right now, example of the failure of isometry in the map connecting the bulk with the boundary are so-called quantum islands. Now, quantum islands are something that appear in the interior of black holes when you're dealing with evaporating black holes past the page time. Now, the page time is basically, if you're familiar with evaporating black holes, a black hole basically slowly evaporates, emits Hawking radiation. The entropy of this radiation rises progressively until it reaches a maximum point, and then it starts going down. This is the idea of the page curve. After the page curve is when the entropy of the black hole starts going down. Now, to make sense of these results, one needs these quantum islands, and these quantum islands have also the funny property that the entanglement wedge reconstruction, they imply that the interior can be reconstructed from Hawking radiation. So this is the example of an island of this sense. So basically, what here is called HCFT is the dual of the CFT, while what is called here WHRAD is the holographic dual of the Hawking radiation. So before the page time, basically, HCFT encodes the entire black hole, including its interior. After the page time, we have this strange behavior whereby HCFT still encodes basically an area around the horizon of the black hole, but then the majority of the interior is encoded in HRAD, which is the holographic dual of the Hawking radiation. If entanglement wedge reconstruction is correct, since this green region is the entanglement wedge of the Hawking radiation, this implies that we can use data, we can use basically the Hawking radiation to reconstruct what is going on in the interior of the black hole. A consequence of this is that you can actually extract information from inside the black hole, and so you don't lose information during black hole evaporation. You basically, to say that this solves the information loss paradox is, of course, an overstatement, a significant overstatement, but at least it solves the problem of making sure that information can actually come out of the black hole and can be recovered from the radiation without having to suppose that anything strange except for this quantum islands is going on. Now, to make these things a bit more precise, we can use a simple toy model that is borrowed from a lovely recent paper by Akers, Engelhardt, Pennington, Harlow, and collaborators. So we'll simply deal with a finite dimensional quantum system. And we will take a quantum system I, which we represent with a Hilbert space Hi. And we can think of this as the finite dimensional analog of the semiclassical description of the interior patterns of Fourier radiation for a fixed Cauchy slice at time t. So basically, Hi is telling us what is going on in the interior of the black hole. It is the Hilbert space of the interior of the black hole. We also define a quantum system B with a certain associated Hilbert space HB, which we take as giving the fundamental non-perturbative representation of the black hole. So Hi is supposed to be a bulk thing in ADS if you want to think of the continuum limit of these things, while B and HB are supposed to be boundary thing points, something that at least as of now we only know how to describe in the boundaries. The map between them is given by, that should not be R, that should be I, but is given by a linear map between Hi and HB, which implements reconstruction of bulk operators in this way. So basically, where an I is a basis for Hi, B is a basis for HB, and these phases are just randomly chosen because the idea here is that the black hole is chaotic. Now, this is reasonably straightforward. Here, the idea is simply that you give me a basis for the semiclassical Hilbert space, you give me a map, I apply the map to my semiclassical Hilbert space, and I'm returned something that is described in terms of the fundamental degrees of freedom, so in terms of this B Hilbert space. Again, these are the bases, then from the basis you can reconstruct whatever you want in the Hilbert space. Now, the interesting aspect of this whole story is that if we take this modulo B to be the dimension of HB and modulo I the dimension of Hi, then V can only be an isometry if the dimension of I is smaller than the dimension of B. If the dimension of B is smaller than the dimension of I, then quite straightforwardly, there are not enough basis states in HB to ensure that V can be an isometry, in the sense that it cannot be a linear map that preserves the inner products. You can kind of intuitively see this, because if I have more basis vectors here in Hi, so if I have more Ni's than B's, then basically I will not be able to just map each basis state in Hi to a basis state in B, and then I won't be able to preserve inner products. What is the case, nonetheless, is that an expression like this obtains for the overlap between two states in the fundamental description. As you see, we are applying the map to both of them, so this gives us their fundamental overlap. And what is going on here is basically that the overlap between them, when they're the same, is 1. When they're different, is very small. That's the trick. We have basically the dimension of B at the denominator, and this ensures basically that these things are going to be exponentially suppressed because the dimension of B is going in general to be very large. You can also, in this simple time model, it doesn't really make sense now to go through this, but you can actually derive entanglement edge reconstruction and islands in this simple model, so you can check just the paper by Akers and collaborators to check this. At this point, it wouldn't really make sense to derive this kind of non-zero but very small, very suppressed overlap is enough for now. Now, this is basically the idea behind reconstruction, expressed in a very simple toy model. Now, I want to discuss something slightly related to this, which is that for states of sub-exponential complexity, the semiclassical description, that is basically the description given by HI, holds up to exponentially small corrections, even when B is much smaller than I. So the idea here basically is that the failures of the semiclassical description, which is these non-zero overlaps, which basically tell me that my original Hilbert space was in some sense mistaken, can be actually hidden behind a computational complexity barrier. So as long as I'm dealing with sub-exponential complexity operations, then I cannot really see this failure of orthogonality. If I am allowed to perform an exponentially complex operation, then I will be able to see this non-zero overlap, and I will be able to see the fact that my semiclassical approximation was really not the correct way to go about things. But the trick is that no actual observer, at least no semiclassical observer, is going to be able to perform anything like this, because in complexity theory, it is customary to associate complex operations with operations that basically cannot be carried out in practice, while the sub-exponential ones, at least in principle in some sense, can. Of course, it might be very hard to even carry out something sub-exponential, but the idea is that an exponentially complex operation is simply something that you cannot do in practice. So the idea here is that failures of isometry go beyond the ability of an observer to detect them. And so you can trust your semiclassical reasoning as long basically as you don't probe too hard, where too hard is defined in terms of computational complexity. Now, another important consequence of these very small overlaps in the fundamental description is that when V is not an isometry, and the failure of V in isometry is in particular relevant to the black hole interior, then bulk reconstruction will be, in general, something that is called state-dependent. Now here, state-dependent basically means that the operators in the semiclassical description only have equivalence in the fundamental description if you assume a specific state. So if we take O to be an operator in the semiclassical description, and O bar an operator in the fundamental description, then this equation, that basically is equation 2, which basically is the condition for something, for an operator to count in the fundamental description, to count as the reconstruction of an operator in the semiclassical description, obtains only if we assume a certain state phi. And if we change the state phi here, then we get different operators, O bar, here. So we'll have different operators depending on the state that we choose. And so for simplicity, we'll write basically, we will add a phi subscript in the notation to make this explicit. So for different phis, there will be different O phis that satisfy 2. The consequence of this is that semiclassical operators are not well-defined operators. In particular, they won't be linear operators in the fundamental description. You can see that O cannot be a linear operator in the fundamental description, because if you give me different phis, I'm going to have different O bars, phi. And so I won't have a single linear operator representing O in the fundamental description. The idea here is basically the following. I have a certain operator, which given a certain state phi and maybe a small subspace of states, behaves like the operator O in the semiclassical description, but outside of this very small subspace, it doesn't. Outside of this very small subspace, I need to choose I need to, first of all, circumscribe a different very small subspace. And then in that subspace, I will be able to find a different operator, O bar, which will depend again on the state that I've chosen. And that operator will again behave for those states like O. And so the basic issue then that you run into is that there is no basically linear way to combine these into single operator. And in particular, of course, this is going to be true whenever the dimension of B is much more than the dimension of phi, which is when non-perturbative effects become relevant. B is not an isometry, and you get all these strange effects in your semiclassical description, such as quantum islands, which have this kind of strange non-local effects. Now, the crucial point here is that there is no contradiction, of course, between state-dependent operators and having a semiclassical description, the black hole interior. There is no contradiction in the sense that the state-dependent operators are required to accommodate the failures of isometry in B, while the exponential complexity of detecting these failures of isometry makes sure that basically no observer will actually be able to check these failures of isometry, and so no observer will actually be able to verify that they are dealing with state-dependent operators. They will just see a semiclassical approximation. They will think that it is fine. Now, if they were able to probe their semiclassical description fine enough to see these very small overlaps, and so effectively to go to the fundamental description, then of course they would see that these are state-dependent operators, and their semiclassical description would basically break down. The trick that complexity makes is that it hides the state dependence and these failures of isometry from the semiclassical observer. This, of course, does not mean that those operators are not state dependent. They are, and they're not linear operators, so they're not well-defined operators in quantum mechanics. Yet, we can at least approximate semiclassical spacetime. Now, said this, and now I'll try to give you an idea of basically what this implies for emergence. Now, let me start by saying something about what I mean by emergence here. Emergence is basically usually understood as a phenomenon that encompasses two prima facie contrasting aspects. One is this idea of autonomy, that emergent entities are in some relevant sense autonomous from or novel with respect to the entities from which they emerge. And on the other hand, the idea of dependence. The idea of dependence is that emergent entities ontologically depend, or if you're a fan of the Nagelian approach that Butterfield and others have developed, these kind of matters, they are derived from or reducible to the microscopic entities from which they emerge. The idea behind emergence is that there should be a relation capable of fulfilling these two roles at the same time, and that this relation is crucial to understanding the relations between entities at different levels of fundamentality. A good example to make sense of how emergence works is a relationship between thermodynamics and statistical mechanics, which very roughly we can characterize as follows. So you take a physical system associated space M. With this physical system, each point P in M is a microstate whose behavior is described by statistical mechanics. So basically, the point P is supposed to be a microscopic description of my system at the level of the constituent particles. Now, we can define in this phase space thermodynamic quantities such as temperature or entropy as functions on this phase space. More specifically, as functions which basically take the same values for more or less large subspaces of M. Basically, what we can think about these new thermodynamic quantities is that the procedure by which we get to them is a kind of coarse graining, because we can only identify subspaces of phase space using things like entropy and temperature, and not a single microstate. Now we can check how this cross graining and thus the relationship between statistical mechanics and thermodynamics can be understood in terms of emergence. And so we start with dependence. Now with dependence, it's almost straightforward, since each thermodynamic property is fixed by fixing the appropriate microstate. And since the microstates are presumably more fundamental than the coarse-grained thermodynamic properties, it seems natural to take the statistical mechanical description to be more fundamental than and to ground the thermodynamic description. Again, if you want to do the Nagelian approach, here you actually need to go through the somewhat non-trivial task of deriving in the Hegelian sense thermodynamics from statistical mechanics. This is somewhat non-trivial, but for our purposes, this is enough. Now moving to autonomy, we can basically run the same kind of argument. Autonomy is obtained because we are basically associating to a single macro state, to a single value for its thermodynamical property, a large variety of different microstates. And so in some sense, these thermodynamic properties are independent of the details of these microstates. In other words, the definition of these thermodynamic properties is autonomous from the detailed structure of the statistical mechanical microstates, and at most depends on their coarse-grained large-scale properties. Now, if you have this example in mind, we can understand why state-dependent operators, and thus the semiclassical description, basically stop you from using emergence when you're dealing with black holes in IndiaCFT. Now we start with autonomy, and then we move to dependence. Now, why is autonomy threatened by state-dependent operators? The idea is that state-dependent operators, if they're there, mean that quantities in the semiclassical gravity description will end up sensitively depending on the details of their fundamental description. Recall the basic idea of state-dependent operators, that I have an operator representing in the fundamental description a certain semiclassical quantity. Only by assuming a state, I need to basically pick a state with all its CFT state, with all its strange properties and all whatever quantum gravity mumbo jumbo is going on. And if I try to basically use a different one, it just doesn't work. I need to use a different operator. Basically, the idea here is that when state-dependent operators are involved, we cannot ignore the fine-grained structure of the fundamental state, which is in sharp contrast with thermodynamics. In thermodynamics, if you recall, the exact point is that I don't need to commit myself to specific microstates to make sense of the thermodynamic quantities. What happens with state-dependent operators is that instead I need to choose a certain microstate to make sense of whatever semiclassical effective description that I want to use. This is the exact opposite of what was going on in thermodynamics. Thermodynamics, I can ignore the details of a microstate because I know that there is a possibly large number of microstates that all do the job. They all have the same thermodynamic properties. When we are dealing with state dependency, it is not the case. The specific operator that I choose, the specific operator that represents a certain semiclassical quantity, is going to depend on the specific state that I need, the microscopic state that I need. So it seems that under no reasonable reading of autonomy, state-dependent operators can be construed as autonomous from whatever the fundamental description. Now let us look at dependence. Now, as I mentioned, state-dependent operators are not linear operators. Now, let us simply assume that a minimal condition for a relation of dependence is that both its relata exist. Now, this seems somewhat reasonable. Ontological dependency is usually taken, at least it's my understanding. Maybe someone here knows more about metaphysics, the metaphysics of dependence than I do. But it seems to me that it's usually taken to be existence entailing. So if whatever is fundamental exists, then what is non-fundamental should exist. And so it seems necessary that both the relata in this case exist. And again, if you want to run the Hegelian version of reduction, this would basically amount to having a formally well-defined operator. Now, if you want to assume this, then also assume that for an operator to represent an actually existing physically well-defined entity, it must be a linear operator. Then space-time in the context of the black hole interior does not specify dependence because state-dependent operators are not linear operators. Now, if you take the Hegelian line, it's somewhat clearer. Linear operators are not really formally proper operators in quantum mechanics. And so they cannot give you basically the kind of formal reduction that you want. One might maybe decide to actually attack this idea that a linear operator is required in quantum mechanics to represent a physically well-defined entity. On this point, it simply seems to be the case that, at least in quantum mechanics, linear operators are always required, and we always deal with linear operators. There might be extensions of quantum mechanics to which include this kind of non-linear operators. It's not clear that anything well-defined for foundationally satisfactory is actually on the table at this point. The basic point seems to be that in this specific situation, and in most of the approaches that exist to making sense of this kind of state dependence, these state-dependent operators are really understood as something that behaves in a certain way when you probe it in a certain way. So it's in some sense an operationally defined quantity. We say that these we're not really defining some proper physical quantity when we are dealing with state-dependent operators. We're simply defining some quantity that, when probed by a certain observer only to a certain depth, it behaves in a certain way, and so it returns certain experimental answers to the questions that you ask of them. But it's not really a proper quantity that represents those things. If you want an analogy with thermodynamics, again, what is going on with state dependence is kind of the following. If you give me, again, a phase space, but now we suppose that this phase space has some kind of string geometry by which basically I can define various subspaces of this phase space, and then I can define an entropy function which is different for each of these subspaces, and I cannot combine these entropy functions into a single function, single well-defined, mathematically well-defined function that gives me, let's say, a global look at entropy. I only have this patchwork of different things that I cannot glue together. Now, in this situation, it seems that the only sensible answer is to say that there is no well-defined notion of entropy in this case. There are simply a variety of restricted quantities that behave like entropy if you don't look too close. But if you look too close, you're going to be able to see that they're not really entropy because they deviate at some point. Okay. So this is basically, again, that say that if we take as a minimum requirement that physical things in quantum mechanics are supposed to be represented by linear operators, and that things should be physically well-defined and exist to be a result of a dependence relation, then there cannot be a dependence relation between the fundamental and the semiclassical description in IndiaCFT. Now, if this is true, then neither autonomy nor dependence are satisfied by the black hole interior in IndiaCFT. And if neither dependence nor autonomy are satisfied by the black hole interior in IndiaCFT, then it seems that we cannot really speak of emergence in this situation. And so it seems that in some sense, emergence is not the appropriate relation to connect the fundamental and semiclassical descriptions in IndiaCFT. And so we cannot say that spacetime is emergent in IndiaCFT. Now, keep in mind that since dependence is violated, we really cannot even just eschew the autonomy constraint and simply say that in some sense, spacetime is grounded in the fundamental degrees of freedom, because of course we don't even have dependency. So it's not really, in some sense, it is much more general than emergence. Now, if you recall from the beginning, the reason why we started looking into spacetime emergence was to answer to the worry about empirical incoherence that Raggett and Woodrick raised for a theory of quantum gravity. So the idea was, if you recall, that a certain scientific theory, in this case quantum gravity, might undermine by its very structure the very same predictions on which a theory relies for confirmation. In the case of quantum gravity, this was because any kind of empirical confirmation that we gain is spatiotemporally localized. But if it is spatiotemporally localized, and the theory that we are confirming says that spacetime doesn't exist, we seem to have a clash between these two conditions. So basically what is going on here is that it is unclear what an experiment would even be, let alone, of course, how to perform it, if we don't have spacetime as a background to define all this. And of course, if, as I mentioned, if spacetime is emergent and thus available, then we can just ignore this issue and account for experimental data using the emergent spacetime and simply ignore the fact that at a fundamental level we don't have spacetime. Now, but the problem that we are facing in this situation is exactly that emergence is not the correct way to think about the black hole interior, but we presumably want to be able to say that the black hole interior has a certain geometry and that someone who jumps into the black hole, however unfortunate their fate might be, is going to actually see something. They're not going to face curvatures, at least for some time. They reach a singularity of they're not going to reach Planckian scale curvature, so they should be able to basically see something that resembles semiclassical spacetime. But in some sense, we cannot really say this because spacetime is not emergent in this situation. So what gives? Well, the idea is that basically what we can do in this situation, if you recall what I've told you about complexity, is that while it is true that space-time as an ontological posit, as an entity, does not really make sense, what does keep to make sense is that an observer who jumps into the black hole, as long as they don't perform anything too difficult, as long as they don't try to perform an exponentially complex, succeed actually at performing an exponentially complex operation, they will actually get the same experimental results as one would have gotten had space-time being there, up to, again, this exponentially complex operation. And this is guaranteed to us by the holographic map. So in some sense, as long as our hypothetical observer is limited to operations of sub-exponential complexity, then their measurements, that anything that they can learn about the world around them, will look indeed perfectly spatiotemporal. They will indeed see space-time in some sense. They will basically perform some kind of operation on a quantum state, and the quantum state will return to them a verdict that is spatiotemporal. So it's not strictly speaking spatiotemporal, actually, but it looks indistinguishable from a spatiotemporal verdict. So in this sense, they will simply avoid empirical incoherence because all their experiments, anything they can do, not even experiments strictly speaking, anything they can do, any operation that they can carry out on their quantum state is going to be mapped exactly to an operation in a semiclassical effective field theory, which is a spatiotemporal theory. It's just that, strictly speaking, space-time is not there, but they cannot really realize that space-time is there. So we can summarize this point in the following criterion that we can call operational recovery. And the idea is that as long as experimental information can be defined appropriately, and so chiefly in terms of the recovery of observables that approximate the behavior of semiclassical gravity, then there is no problem of empirical incoherence independently of whether or not spacetime is emergent. Basically, empirical incoherence is concerned with experiments, and basically, so far as it's concerned with experiments, it's concerned with observables. As long as I can recover the observables, I don't really care that then I can say that in some metaphysically loaded sense, space-time is there. I don't really care. I have my observables. I have my experimental procedures available to me. I can act on my state. Now, the question is simply, is the state responsive in a way that I can make sense of? And the state is indeed, in this case, as long as the observables are appropriately recovered, the state does respond in an appropriate way. So there are two ways to make sense, I think, of this situation, which basically depend on whether or not you think that this kind of operational data that we can define in terms of observables and probability distributions for observables is sufficient or not to basically define space-time. So you either have what I call operational eliminativism, and operational eliminativism basically says that there is no such thing as space-time, but rather there are quantum gravity degrees of freedom, that give an arbitrarily good approximation to the observable data that would be typical of a space-time theory, thus avoiding empirical incoherence, again, because we arbitrarily approximate the relevant operational and observable data that we are after. And then you also have operational emergence, which says that if prior to all of this, you reduce space-time to a certain pattern of experimental data, then you can speak of emergent space-time because complexity hides the non-isometric natures of the holographic map. And so the observational data, strictly speaking, does not depend on the fundamental state. And so you avoid both empirical incoherence because you still have the relevant observational data, but you also can speak of emergence because this complexity wall basically makes sure that your operational data is not significantly dependent on the fundamental state and is thus isolated from the non-spatiotemporal goings on. So let me just briefly, to conclude, speak a bit about how autonomy is guaranteed in operational emergence. You can kind of basically tell the same story about dependence. So I'll just speak about autonomy. Autonomy in this context is guaranteed by the fact that, again, up to exponentially complex operation, a description in terms of semiclassical gravity will be acceptable. If we limit ourselves to such operations, as a semiclassical observer indeed is forced to do, then there is no need for a fundamental description. We can simply describe our operations. As long as we basically can only deal with sub-exponential operations, then we can really just use semiclassical gravity. We don't need an input from the CFT. We need the input from the CFT if we want to describe arbitrarily complex operation. Now, the reason why this is operational and why we must restrict ourselves to operational data and to the operational data available in semiclassical picture is that complexity theory does not really deal with in principle things. It is with in practice constraints. Complexity theory basically tells you what you can or cannot do concretely on a system. It's not really in the business of telling you what things are in principle or telling you the ontology of something. It's just in the business of basically telling you that if you can or cannot carry out a certain task given concrete real-world resource constraints. So in particular, we would be mistaken in saying that there is emergent space-time in the sense of a four-dimensional manifold, because this description is just not well defined. We have state dependence, and the only way that we were able to use the semiclassical data was by taking this kind of restriction given by complexity. Again, it is sensible to use complexity to restrict our observations because that is what complexity deals with, concrete operations that can perform concrete tasks. But complexity theory simply, it would be in some sense a category mistake to try to apply complexity theory to the definition, to an ontological understanding of something like space-time, simply because complexity theory does not deal with, in some sense, the ontological status of space-time. It just deals with whether or not you can measure something. But we can speak in some sense of emergent space-time insofar as we have a certain pattern of observational data, and we can use that observational data to then define whatever space-time theory we're interested in. But ultimately, we are only restricted to that and just reducing space-time to a certain pattern of observational data, because that observational data is, thanks to complexity theory, well defined, and it does not depend sensitively on the fundamental description. So to conclude, I've kind of tried to give you an idea of why this idea of space-time emergence fails in IndiaCFT, and why we can only make sense the appearance of space-time in some kind of operational way. Now, there are definitely open questions here. One thing is that to make, in particular, something like operational emergence work, we do need an analysis of space-time in operational terms. Now, thus far, I just simply assume that you can do something like that. You can reduce space-time to operational data. Now, of course, to actually make something like that work, you would need to construct an operational reduction of space-time. It seems that operational recovery has something to say about the relevance of global space-time structure in general relativity for quantum gravity. This is somewhat unexplored area. It's sometimes get mentioned in papers on foundations of GR, but it's always left a bit unexplored. And what operational recovery seems to say in some sense is that if you cannot measure it when you're dealing with semiclassical gravity, which is where these kind of global constraints are supposed to be found, if you cannot measure it, then it's not there. For global structure, this suggests that a lot of the worries about global structure in GR might indeed be misplaced because we cannot actually have empirical access to them. And then, last but not least, would be to have an actual interpretation of state-dependent operators, which would be able to give some reasonable foundations to this new object that have come to play quite an important role in both quantum gravity, and they can become relevant, at least they are suggested to be relevant also for simple effective field theories in condensed matter. So it would be nice to have some kind of foundational description of these things that can kind of give us an understanding similar to standard linear operators. Okay, and that's it. Wait. Okay, thanks.
Well, thank you very much, Enrico. It was impressive. I mean, you touched so many topics. So
I hope it was not too much through the force through a lot of holography.
It was dense, let's say. But,
yeah.
I guess that I mean, people can also ask questions, clarificatory questions in case. Are there some questions? You can raise your hands, of course. Nobody's asking questions. Alvaro. Carlo.
Yeah, like, hi Enrico, nice to see you again.
Hi Alvaro.
Thank you for the talk. Let me clarify a thing. What do you mean by semi-classical gravity or semi-classical theory? Is it a theory in which gravity is classical and you have like on the right hand side of the Einstein equation like the expected value of your matter fields or something like that?
Basically, in this literature, what people usually mean when they speak of when they speak of semi-classical gravity, they basically they actually mean something slightly more expansive than that. Basically, by semi-classical gravity, people mean a perturbative expansion powers of G of general relativity with H-bar corrections also. Okay, so you're basically taking just a perturbative treatment of general relativity.
But is gravity in any sense quantum or?
Yes. Yes, okay, it's supposed to be. It's supposed to be quantum general relativity. So let me step back. So what is going on here is that you take basically the Lagrangian limit of the CFT. So you have this duality, which holds basically for all. You have quantum gravity in the bulk and the CFT in the boundary, and you have fully quantum gravity in the bulk by construction, and you have this field theory. Now, what you do is that if you take basically the Lagrangian limit in the CFT, this is equivalent basically to taking the limit for G that goes to 0 in the bulk, which gives you back basically quantum field theory on some kind of curved background. And then you reintroduce basically back reaction, and you reintroduce a dynamical metric by adding corrections, which are in the CFT in powers of 1 over n, and in the bulk they are in powers of G. So you also have quantum gravity.
Okay, so your Hilbert space, this it's I was a Hilbert space with matter and gravity and everything.
I cannot hear you very well, Alvaro.
Sorry. I don't know if my mic is here. Yeah, I was saying that your Hilbert space, this HI you had, it is a Hilbert space with matter degrees of freedom, but also gravitational degrees of freedom. Okay.
Yeah. There are supposed to be yes, some kind of graviton that gets quantized.
Thank you.
So it's Carl.
So I had a few questions, but maybe I can start with one of clarification. You mentioned at the beginning that, of course, we live in de Sitter spacetime, not anti-de Sitter spacetime. And then you said something that was meant to make it sound like, but that's okay, we can still pursue, learn something about the real world from all this IndiaCFT stuff. But I've never understood that, and I didn't understand what you were saying about that. So if you could explain why.
Yes. So basically, I'll first say the official line, then I'll say a slightly more speculative line. The official line is that something like, for example, entanglement wedge reconstruction is supposed to really give you the relation between some kind of quantum system, between some kind of fundamental quantum system and a semiclassical description which includes gravity. So in that sense, you expect that something like this should hold in more general theories. Now, there is no concrete construction, and there are some obstacles to developing a concrete construction in cases different from ADS. But the basic idea is that some of these results, computations of the page curve, to some extent islands, should generalize beyond the ADS case, because something like this does not seem to depend very sensitively on properties of ADS spacetime. Maybe here the only thing that is really dependent on ADS spacetime is that we have the CFT here, and we have a CFT because the boundary in ADS gravity basically disappears. And of course, in the Sitter spacetime, this will not be the case. You will need to extend this to weakly gravitating regions, and that is somewhat difficult to do. But in principle, it seems that something like this is much more general than IndiaCFT, and so it should, in principle, apply also to those cases. This is basically the official line. A slightly more speculative line is that this map here, this map V here, now I've not described it in this way, but it's really it's a quantum error correcting code. And this claim that is a quantum error correcting code, then the failure of isometry basically means that it is an approximate quantum error correcting code, because there are errors in the reconstruction procedure. Now, the interesting thing is that approximate quantum error correcting codes do encode, at least have some kind of pretty tight relation with the renormalization group. So you can, in some sense, try to make sense of the relation between different energy scales that is given by renormalization group flow as a kind of approximate quantum error correcting code. That's at least something that is sometimes claimed. Now, if something like that is true, then you see kind of straightforwardly that these ideas are simply just giving you some kind of way to study basically the semiclassical regime of a quantum gravity system. The only reason why you end up using IndiaCFT is because you have a lot of, it's much more easier to define the fundamental quantum system when it is just a CFT and it has no gravity than more complex equations. But really what you're doing here is that you're studying properties of the renormalization group flow in gravity. The third way to kind of see this point, that I think has been emphasized by, among others, by David Wallace, though I don't know if it's in print, it's that you can think of ADS as basically taking an asymptotically flat spacetime and putting it in a box. You put it in a box, and by putting it in a box, you basically regularize infrared infinities. And now at this point, all that you're in the business of saying is that IndiaCFT is really just a way to basically do quantum gravity for any system that we can idealize as something that we put in the box. And of course, if the box is large enough, any system except the whole universe can be seen like this, because if you're far away from boundaries, if our system is in the middle and we are far away enough, then the boundary is going to be, in some sense, not crucial to this whole story. So that is something that I've heard David Wallace sometimes mention. So the idea is that you just put your particle system in the middle, you're far away enough, and then you can do whatever you want in quantum gravity in this way, except cosmology. Cosmology is the only thing that you cannot do because you cannot really put the universe in a box. It would be somewhat strange to be able to put everything inside something. So these are kind of three ways to think about the sense in which IndiaCFT is supposed to teach something. Of course, none of these ways is, let's say, it's not a proof that IndiaCFT is going to be relevant to quantum gravity in general. To some extent, it is an open question. These are just ways in which it should, in principle, be relevant. Then, of course, it might be that just your project has some kind of some fundamental flaw that makes it inapplicable to anything beyond the IDEA space-time, and so it's really irrelevant to anything else. But at least as far as I know, no flow of this kind.
Okay, thanks. That helps a bit.
Okay.
So are there other questions, remarks? Then I can see Luca Zambelli, who's online, who's a physicist. So, and Brukayan.
I have too many questions. I can't choose which one I should ask. Maybe I will start with one. It's more of a curiosity. So this idea of the complexity bound, which becomes crucial for the emergence of space-time or of anything, is, I mean, to me, it is very much reminiscent of other bounds. Like, for instance, the simplest one is, if you remember, the idea of Maxwell's demon. You put a bound on how much information you can gain on something, and that leads you somewhere else. So lots of these ideas have interpretations in terms of coarse graining, as you said, and RG flows. So I was wondering if there are studies in this scientific community which have tried to interpret these bounds on complexity as, in the end, again, RG flows and coarse graining processes.
Yes. So I'm not entirely sure of the complexity bounds. As I was saying before, the quantum error correction, which is this V, can be mapped to a kind of RG flow. I'm not entirely sure how this kind of complexity bounds would fare into that model, mostly because the ones that, so let me go out on a limb. So I'll say this. What as far as I know, has not been studied in a lot of detail in this literature, but I might be mistaken, is what happens when you have this kind of failures of isometry. So you find connections between approximate quantum error correction with RG flow, but my understanding is that in most of those cases, the approximate claim is actually that the failure of isometry is very small. Now here we have actually reasonably large failures of isometry. This is why they actually can become important. I don't know that there is any interpretation in terms of something like RG flow of this kind of large scale failures of isometry, and consequently of the complexity bounds. My impression is that if these kind of failures of isometry are to be interpreted in terms of RG flow, they probably are something like failures of naturalness, some kind of failure of separation of scales, basically. But as far as I know, there is no like detailed paper on this. So that would just be an hunch. My impression is that they probably have to do with that, but I'm not aware of any very detailed derivation that shows that indeed these are somewhat the same things. And of course, then if just to again go out on a limb, if that is the case, then you interpret basically the complexity bound as some kind of restriction that tells you that for a certain class of observables, you can just ignore the fact that you don't have separation of scales, so you can, in some sense, trust your effective description, even if, in some sense, you really shouldn't.
Yeah, maybe just to help making it more precise. Do you know if it has been studied whether the isometry error, as you call it, depends on the black hole temperature and entropy?
Oh yeah. Yes, that is actually, so you can find some details on this in this paper. Wait, let me pull up the reference. So that part you can. Here it is, this one. This is kind of, I think, the state of the art on this kind of constructions. It is a finite dimensional model, all the caveats apply. But yes, I didn't put it here because it ends up becoming just a long equation, which is not immediately readable. So it didn't really make sense in a presentation to put it. But you can actually quantify the complexity of detecting the overlap, and you can see that it basically scales with it is exponential in the black hole entropy, so it depends on the black hole entropy. That in some sense, if you're familiar with black hole evaporation, that kind of tells you why you kind of have these islands here and you can see them, because and why you have this kind of wait. Okay, so here you can see here that if you basically try to probe something whose an operator of size is around the black hole entropy, then basically you're going to be able to see this kind of small overlaps, and so you're going to get all the effects. So in some sense, that is the idea. But yes, I mean, if you go and check their paper, the actual formula that they derive for the complexity tells you that it's not strictly speaking the black hole entropy, because it's this B, which is finite dimensional. It's all done in quantum information, but it's the analog basically of the black hole entropy. Does it help?
Yeah, probably it is it is one way of making it more precise. The idea in the background is that often you can define emergence as something which is related to the idea of how do the properties of my system change when I change my coarse graining scale. And in several cases, even if it looks there is no scale, actually you can use informational data like entropy or complexity as a scale. So maybe in this sense, you might reinterpret what you call isometry error. Was it isometry error?
Yeah, you basically you have failures of isometry.
Yeah, isometry failure as a scale, and in the limit of a certain and a certain limit in this scale, then your data your effective description emerges. I don't know, because it looks. If I understood you correctly, you use the language which is very polarizing. So no emergence because because there is this other key ingredient. But in a sense, you could see that ingredient as part of an emergence picture. That was my doubt.
So I would say two things. So one is just that I would actually be interested in seeing how you can use some I'm not sure that I fully understand the idea of using complexity as a scale measure, but that is just me. I mean, I would need to actually check how that works. my suspicion, at least in this context, would be that you still run into, if you want to use complexity as kind of scale factor, the issue that I guess you would run into at some point is the following: that the problem is that complexity at its core does not really. How can I put this in a way that is okay? So what people are somewhat interested when they speak of spacetime emergence, and what was at stake here was this idea that, in some sense, people sometimes call it this. You can call it ontological emergence. The idea is that there is a further entity, which you can call spacetime, that you need to commit yourself to. So you have this fundamental level, and then you have another thing, and then you have a relation between them. This other thing is just spacetime. Now, the problem with using complexity as the scale measure is that complexity is really a measure of whether or not you can do stuff. So it's a measure of whether or not you can detect something. You can perform a task. A measure of being able to perform a task, and so the idea that in a certain limit where, for example, I am allowed to perform only very simple tasks, can give me this kind of ontological emergence, seems to be indeed at odds with the idea itself of ontological emergence, the ontological part. So the idea is that, in some sense, whether or not spacetime is there would end up depending on whether or not I am basically skilled enough, where the skill can be an objective thing, but in some sense it's going to depend on whether or not I'm skilled enough, and I'm the type of observer that is skilled enough to perform certain tasks. Not really on whether or not that thing is there. If I can perform a certain task, then spacetime is not there. If I cannot, then spacetime is there. That seems to go against the idea that things, in some sense, should exist on their own. I don't know if this is coming through. So the things should not depend on their existence or whether or not we are computationally skilled enough, even if the bound on our computational skill is, in some sense, objective. It is still a practical limitation. It's a limitation of resources. It's not that the computation cannot be completed, it's just that it takes an enormous amount of time. Here it takes an amount of time of the order of the black hole entropy. That's basically the worry. But I will need to check how you can use complexity to how can you use complexity as a coarse-grained measure. I mean, maybe I'm just misunderstanding how it's supposed to go, but at least how it goes in this kind of constructions, it seems to me that you kind of at some point always end up with something like that.
Okay, well, I think I should stop here because I have too many questions, and I guess we don't have time to ask all of them. So. But thank you very much.
You're in touch now. You can write to Enrico in case you can have correspondence. Are there other questions or remarks? I have actually one. So Enrico, you clearly pointed out your position with respect to emergence. However, we know that today in the debate, there's not just the problem eventually of defining what emergence is, and in which context, of course, and according to certain approaches to quantum gravity, for example. But there is also this topic regarding, it's a pity that Giuliano left the meeting, because there is also this topic of the disappearance of time that is discussed in the literature, or at least is now more discussed in the literature than before. So I clearly see your point for emergence. What about, what could you say with regard to eventually the disappearance of time in the context of your analysis of black holes' interiors?
So well, there are a couple different things I think that one can say. So there is a somewhat not satisfactory answer, which is that the CFT that we are defining everything from has time in it. So in some sense, you do, in both cases, you do have some kind of time parameter. And this is just, but this is not satisfactory for two reasons. One is that it's not really fun. And the second reason is that this would be something that is really, really, really strictly dependent on ADS. So you have this kind of boundary time in ADS because of the boundary itself is time-like. But this is not something that is, for example, it's not true in flat space-time, and it is not true at all in the Sitter space-time. So some sense, this is not really the best way to go at this kind of question. In purely technical terms, these models are again fine in the sense that you can prove now. Here I use a static model again because it's simpler. So we are just fixing a certain Cauchy slice at a certain time t, boundary time t. But you can prove you basically deal with some. They do it in the paper. You use some more complex machinery, and you can prove that basically the holographic map V commutes with the Hamiltonian of the CFT. So it's not touched by dynamical evolution. Now, one thing that is interesting that has been studied quite a bit in physics, it has not been studied a lot, I think, in philosophy. It has been studied by some people that work actually on algebraic quantum field theory. Is that one of the conditions for entanglement wedge reconstruction to hold? So you can prove again. There is I think that Arlo in his review mentions this, but there is a long line of theorems that shows this at greater and greater generality. You can prove that the validity of this statement is equivalent to the fact that the relative entropy in the boundary is the same as the relative entropy in the bulk. Now, what this means is that the relative entropy, this means is that the modular Hamiltonian flow in the boundary matches the modular Hamiltonian flow in the entanglement wedge. And what this means, again, is that you can use this modular flow. In principle, there are suggestions you can use this modular flow to define time, to define a notion of time. This will suggest, among others, this has not entered into the holography literature, strangely, but the original suggestion, I think, for this connection was due to Rovelli. So it's called the thermal time hypothesis. It has the connection with time has entered, so you can find quite a bit of papers that suggest that basically this matching of the modular Hamiltonians on the two sides gives you a notion of you can use that to derive a notion of time in the bulk, and so to recover time in general relativity. And then once you have that kind of machinery, then in some sense you just can stop worrying about time at the fundamental level, because at the fundamental level, while time might not be there, you're always going to be able, as long as it is some kind of normal quantum theory, to define this kind of modular flow. This is just a thermodynamic property. So
well, I was not thinking really about the thermal time hypothesis and relative entropy. I've worked about it with Farhan, who's not here today, but I was more thinking about those studies on asymptotic silence in black holes and all those models in which we find the collapse of the light cones, and in a sense, even if we are not discussing these type of studies, still this type of approaches, still I think that there is something to be clarified with respect to what we mean by emergence. And I think also that what Luca Zambelli was suggesting before was interesting. But I think that when we talk about disappearance of time, if any, but still, we are really addressing a different issue from a methodological standpoint and also from a mathematical standpoint. I don't know if you agree with that. And in a sense, your talk proves that or your toy model, the toy model that you discussed proves that it's possible to describe regions of black holes interior. So it's possible to, let's say, give different accounts of the same system, and depending on a sort of a name that we attach to the model, we talk about emergence or disappearance eventually. I don't know if I explained myself. It's a little bit, you know, sort of I don't know if it's clear. Maybe we can chat about it another time. And it's also a long discussion because
I mean, certainly it sounds very interesting. So I'll preface this by saying that I don't know the technical relation between this kind of constructions and the one that you are discussing. So I cannot give any pointers on that. I do agree on the main point that in some sense, when we speak of the emergence of time, there are two things that are going on. There is a sleight of hand and there is a substantive issue. So the sleight of hand is that in some sense it seems that if space-time is emergent, time should be too. But of course, the issue there, the substantive issue is that when you speak of space-time emergence, what you're really interested in is in some sense how to describe geometry and the emergence of geometry from something that is in some sense non-geometrical. Now, that is fine, and that is what I was most worried about here. But of course, you can have a further issue, which is that how can I describe dynamics from something that is not dynamical? And that seems closer to what people are worried about when they speak of the emergence of time. I don't really know. My main problem with some of that literature, it's not even a problem. Like my main worry about some of these issues is that at least I have not found any like technical, like concrete model that I can look at that kind of gives something that is reasonably close to what I would want to see, to be able to say something concrete about what happens when time emerges in this sense. So when you have like dynamics emerging in this way, the closest thing again that I know of what I was mentioning before, but it's very preliminary as far as I know, and so that's my insight. So ultimately, I agree with the basic point that it's really something different from space-time emergence, and it's something in some sense much more worrisome if quantum gravity is supposed to involve emergent time and emergent dynamics in this way. It's kind of conceptually, I think that conceptually most of the worries about space-time emergence in some sense have been eviscerated, so we kind of have an idea of
pardon me, so you're saying that is worrisome, the consequences of or the implications of the disappearance of time rather than the emergence, you would say?
I think it's just very difficult to get a grip on what disappearance of time and to some extent the re-emergence of time, at least in some approximate way.
No, but my point is that it's not that. So what if we discover, so to speak, that these two terms, or what we define as disappearance or emergence, in reality depends on the mathematics you're using, the mathematical methods that you're using, and we talk about disappearance, but in reality it's not disappearance, it's, I don't know, collapse of the light cones, or, you know, it's it's a context in which so it's a sort of a regime in which classical time is untenable, let's say, or where you have maximally decoupled points, for example. You have asymptotic silence near the singularity, and and in a sense, we're not talking about emergence. It's clear we're talking about a more radical, or if you like, radical condition that is very well behind or beyond better it can point to, I don't know, approaches something like approaches like quantum gravity, or it can, I mean, even in asymptotic safety, we have or at least we have studies on asymptotic silence. So, and it's clear that anything that can be, or anything that responds to this is something that, so it's something in which time cannot play any role. And the point, and this is something I'm working on right now, is there any possibility, for example, through the latest studies on quantum information theory, to model these regions near the black hole, near the black hole singularity as regions where we have entanglement, yes, no, maximal entangled states, yes or no, in which sense, blah, blah, blah. But this is another issue. What interests me is rather the fact that depending on the way in which, and depending on the mathematics and the mathematical methods that we use, we either obtain the disappearance of time, or what people call, in a vulgar term, let's say, emergence of time. But it's just, so to speak, it's a matter of confusing, let's say. So it's a matter of confusing the results that with your mathematical methods you obtain with or you are attributing, let's say, to something that is the result of a mathematical method. You're attributing ontological existence, or you are attributing you're surcharging it, let's say. Let's put it in this way. I don't know, it's complicated, and
so the idea would be, let me try to rephrase this. So the idea would be that you have some kind of let's say some kind of abstract construction where you cannot define a time parameter, right? But the question then becomes, okay, so is this failure of the time parameter to be there something that is actually out there in the world, or is it just the case that, yes, the mathematics in some sense leads you to the conclusion that you don't have anything nice enough to be called time, but that's really more an artifact of the fact that you're basically, time in some sense is there. It's just that you're putting too much constraints on what time is supposed to be, and so you're ending up, you're getting to the point that you cannot just you cannot find it in the formalism, but it's there in some sense. Is that fair?
It can be in this way, or it can be that when we have a description of regions such as those emerging in studies on asymptotic silence, we need a notion of a temporality.
Okay.
Say what's going on, let's say, which is so, and this is but interestingly, with regard to space, it's more complicated. Even when you're with regard to space is different. So, for example, in this case, you must have a sort of, let's call it proto-space or something like that. Anyway, even very close, let's say, near the singularity, but not time, not necessarily time. Anyway, it's complicated. I think that your talk was wonderful in the sense that it gave us the chance to discuss many things, and I really hope to see each other in person and
Hopefully.
to see many of the people who are connected now to this meeting very soon. And I would like to thank you very much, Enrico, again for your
Thanks a lot. It was a pleasure. Yeah, hopefully there will be occasion to do this in person. So no, it was a pleasure. Thanks.